Alright, welcome to this chapter. Chapter 4 of your course is dedicated to diagonalization. So diagonalization involves diagonal matrix, okay? And what is a diagonal matrix? We saw it in the previous chapter that a diagonal matrix is a matrix where the non-diagonal elements are zero. So here is an example of an n by n diagonal matrix. So you can see that all the non-diagonal entries are zero. The diagonal entry here can be zero. That is not our focus. Our focus is that the non-diagonal element should be zero, okay? This being said, Aij is equal 0 for I different from j. So this is the definition of a diagonal matrix. So we want to use this diagonal matrix to solve a system of differential equations. So as example, we are giving this system of differential equation. So I can choose to write it as follow: x prime 1, x prime 2 is equal a matrix. I'll call it matrix A. This is 2 minus 1, 5 minus 4. This matrix is multiplied by x1 and x2. This is the matrix A, and let's call this guy x prime, and this is x. So we can write this as x prime is equal ax. Alright, if we introduce a new variables here, let's call this new variable x equal py. Then if we differentiate this, this is x prime is equal p times y prime. And we know that x prime is just given by a times x. Okay? I'm still coming back to explain what is p, because we have to know what is p. So if we then multiply these whole things by the inverse of p, because p is a matrix here, this is also, if we substitute x here, this is, and only remain with y, this is a times p times y. So basically we have p y prime is equal a times p times y. Alright, if I multiply this by another matrix, the inverse of p, under the assumption that you can find the inverse of p, then this is p inverse. So we know that p times p inverse is identity matrix. So we remain here with identity times y prime is y prime is equal to p inverse times a times p times y. This is what we have. Now let's go back to the matrix A, capital A. This matrix capital A is very important here. We have to find the eigenvalue of this matrix. We want to know the eigenvalue associated to this matrix. So by definition of the eigenvalue, this is 2 minus lambda, 5 minus 1 minus 4 minus lambda is equal 0. If you solve this, you find that lambda is equal 1 and lambda is equal, this is lambda 1 and lambda 2 is equal minus 3. From this eigenvalue, we can form what we call the diagonal matrix D, made of this eigenvalue 1, 0, 0, minus 3. This is a diagonal matrix. As we define a diagonal matrix here, you can see that this is exactly an example of a diagonal matrix, right? So we basically just use the eigenvalues obtained from this. Now the matrix P is a matrix obtained from the eigenvectors. So I know that at this stage you don't know what is eigenvalue or eigenvectors, but don't worry, in this chapter or in the next videos, you'll be able to understand what is the eigenvector. I'm just explaining why the concept of diagonalization is very useful for you to solve system of equation like this. Okay? So let's see. To obtain the matrix P, we use this eigenvalue. So if the eigenvalue a minus lambda I times x is a vector is equal 0. So if you substitute here by a1, this becomes 2 minus 1 is 1, 5 minus 1 minus 5 times xy is equal 0 vector. Okay? So solving this, we see that x minus y is equal to 0. It means x is equal y. So from here we can write the eigenvalue v1 is equal 1, 1. So we do the same for the second eigenvalue, and we see that v2 will be 1, 5. All right, from this we form the matrix P such that the matrix P is equal 1, 1 and 1, 5. So the inverse of this matrix, the 2 by 2 matrix, is just 1 over the determinant. The determinant of this is 5 minus 1, this is 4. And the inverse, the transpose is 5 minus 1 and 1. At this stage, this is what we have as inverse. So if I take this inverse, the inverse of this matrix, and I multiply by the matrix A, and I multiply again by P, this is P inverse times A times P. P inverse here is given by this. Let's take it like this. The matrix A is 2 minus 1, 5 minus 4, and the matrix P is 1, 1, 1, 5. This is what we have. So if you multiply this, you obtain exactly 1 over 4, 4, 0, 0, minus 12. So this is our matrix D. This is 1, 0, 0, minus 3. This is the matrix D. This becomes D. This is the matrix D. Is equal D times Y. And we know that D is 1, 0, 0, minus 3, Y1, Y2. Okay? So this is also Y prime 1. So this is vectors, Y prime 1 and Y prime 2. So we have to solve this system. Y prime 1 is equal Y1 and Y prime 2 is equal minus 3Y2. So solving this system becomes very simple. This is Y1 is equal alpha times e to the power t, and Y2 is equal beta times e to the power minus 3t. Alright, this is what we obtained. From this, we can use this, go back to the original variable. It was x. We know that capital X here is P times Y. We already have Y and we know P. This is P times Y. We know P. P is this matrix 1, 1, 1, 5 times this guy. This guy is Y1 is alpha times e to the power t, and this is beta times e to the power minus 3t. Okay? If we multiply this, we obtain x1, x2, multiply this is alpha times e to the power t plus beta times e to the power t minus 3t, and alpha times e to the power t plus 5 beta times e to the power minus 3t. We can simplify this as alpha bracket 1, 1 times e to the power t plus beta times 1, 5 e to the power minus 3t. So this is the solution. So this is the solution to this system of ordinary differential equations. So this example was just to illustrate how useful the concept of diagonalization is in solving the system of differential equations. Don't worry, for the matrix D and P here, they all come from the eigenvalue and eigenvectors. So in the previous video, we explained how to obtain the matrix D and matrix P, okay, from the eigenvalue and eigenvector. So see you in the next video.